Training a deep neural network usually feels straightforward. You watch the training loss drop, you wait for the test accuracy to climb, and you call it a day. But every researcher in this field has stumbled across the weird exceptions. You know the ones. The model perfectly memorizes the training set, yet test accuracy sits at chance level for thousands of epochs. Then suddenly, generalization snaps into place. We call this grokking. Or maybe you've seen epoch-wise double descent, where test error rises and falls in a non-monotonic dance while training loss keeps dropping. These aren't just quirks. They're symptoms of a deeper mismatch between what our standard metrics tell us and what's actually happening inside the model. Today, we're breaking down a rigorous new framework that dissects these phenomena by splitting the learning process into two competing speeds: representation learning in the encoder and readout calibration in the final classifier. The core insight is deceptively simple. Any neural network can be mathematically decomposed into two distinct components. First, a nonlinear encoder, which we'll call phi theta, that maps raw inputs into a high-dimensional representation space. Second, a linear readout matrix, W, that maps those representations directly to logits. The full function is just f of x equals w times phi theta of x. This isn't a new architectural trick. It's a deliberate analytical lens. By isolating the encoder and the readout, we can track their dynamics independently throughout training. The encoder is responsible for feature learning, which means reorganizing the representation space to make classes separable. The readout is responsible for calibration, which means adjusting its weights to exploit whatever geometry the encoder currently provides. The critical realization is that these two processes operate on fundamentally different timescales, and their relative speed dictates whether generalization looks sudden, delayed, or non-monotonic. To measure this, we need task-agnostic diagnostics that go beyond loss and accuracy. We're using 4 specific geometric and kernel-based measures. First, critical dimension, denoted n sub crit. This comes from manifold capacity theory. Roughly speaking, it's the minimum projection dimension required to preserve linear separability of class-conditioned representation manifolds with high probability. Mathematically, it's tied to the expected distance from a random Gaussian direction to the convex cone, spanned by the class manifolds. A lower critical dimension means the manifolds are more untangled and robustly separable. Second, we use a suite of geometric measures from glue theory, which stands for geometry linked to untangling efficiency. This includes effective manifold dimension, effective radius, and center and axis alignment. These decompose the geometry of the manifolds into intraclass spread and interclass orientation, giving us a fine-grained view of how separability actually improves. Third, linear probe accuracy. We freeze the encoder and train a fresh, regularized linear classifier on top of it. The gap between probe accuracy and the actual model's accuracy tells us exactly how well calibrated the readout is relative to the encoder's output. Fourth, last layer, NTK-label alignment. This measures the centered kernel alignment between the feature gram matrix and the label kernel. Under gradient flow on a frozen encoder, this alignment is directly proportional to the initial rate of loss decay. It tells us whether the current feature geometry actually supports efficient linear readout learning, or if the readout is fighting against a poorly structured feature space. Let's apply this to grokking. The dominant narrative, the lazy-to-rich hypothesis, frames grokking as a binary phase transition. Early on, the network is lazy. The neural tangent kernel stays fixed at initialization, features don't move, and the readout does all the heavy lifting. Then, at some critical epoch, the network switches to the rich regime, features reorganize, and generalization emerges. Our diagnostics completely refine this picture. When we track critical dimension throughout training, we see it decrease gradually and continuously from epoch 0. Representation learning is not silent. It's just slower than the readout. In fact, we can quantify a train test gap in NTK alignment. Before grokking onset, the readout's gradient updates are heavily biased toward the training distribution. The readout locks onto memorization shortcuts because the encoder hasn't yet structured the representation space well enough to support generalization. The readout is overfitting at the linear layer. Generalization only emerges when the encoder's gradual untangling finally catches up, forcing the readout to recalibrate its direction. The abrupt jump in test accuracy isn't a sudden change in the encoder. It's the readout finally aligning with a representation that actually generalizes. We also see that different architectures achieve this untangling through qualitatively different geometric pathways. MLPs tend to decrease center alignment and increase axis alignment, while transformers do the opposite, yet both converge to the same functional outcome. This decomposition also cleanly diagnoses epoch-wise double descent, which is often induced by label noise. Standard loss curves make this look like a mysterious non-monotonicity. But our diagnostics reveal a two-stage failure. First, the representation quality actively degrades. Linear probe accuracy drops while critical dimension rises, meaning the manifolds are becoming more entangled rather than untangled. Second, the readout becomes misaligned with the true task signal and starts optimizing for spurious correlations in the noisy labels. We can flag these exact failure modes with 4 diagnostic signatures: readout overfitting, representation degradation, suboptimal readout performance, and spurious alignment where the NTK alignment with noisy labels exceeds alignment with clean labels. Remove the label noise, and both the double descent pattern and these signatures vanish. The framework proves that what looks like a fundamental learning regime shift is often just a diagnosticable mismatch between encoder quality and readout calibration. Why does this matter beyond explaining synthetic benchmarks? Because it gives us a top-down, task-agnostic vocabulary for mechanistic interpretability. Circuit-level analysis is powerful, but it doesn't scale across architectures or tasks. The representation readout decomposition provides principled criteria for when and where to look. It tells us whether a generalization failure stems from poor feature geometry, readout miscalibration, or spurious signal domination. As we push models into safety-critical domains, the ability to distinguish genuine representational progress from memorization artifacts isn't just academically interesting. It's a prerequisite for reliable training diagnostics. The next time you see a flat test accuracy curve followed by a sudden jump or a non-monotonic test error dip, don't just watch the loss. Look at the geometry. Look at the alignment. Because underneath the surface metrics, learning is almost always a negotiation between two speeds, and only by decomposing them can we truly understand what the model is doing.